Welcome back, I'm Scott. This is the second episode of Cubing in a Group, the Cube Group. Today we'll introduce what is a group in a group theory and how we can understand a Rubik's Cube by language from the group theory. Okay, let's start our journey. First, there was nothing on the earth, and God said, "Let there be a Rubik's Cube," and there was one. But what God created was a cube that is already solved, and all the cubies are in their just right position such that every cubie on each surface of a cube has the same color. God decided to name this completed cube as zero, and since we firmly believe that all patterns of a Rubik's Cube come from zero, which we will later explain why, we believe that all other patterns start from zero, which is the basis of the cube world. And now the god wanted to play. He turned the rightmost layer clockwise by 90 degrees, and he got another pattern. For simplicity, let's denote this operation as the letter R, which stands for right. That breaks the sense of unity, like the beauty of the cube, so the god wanted to move back. He turned the rightmost layer of the cube counterclockwise by 90 degrees, and it works. Everything was back to normal, and God then assumed that every action he did on the cube is reversible just by simply reversing each step in order. We denote the counterclockwise notation of the rightmost layer as R prime. And this was the first discovery of God, and he left the rest of the mystery to human beings. Today we find that we can put a cube in a fixed position and conduct six kinds of operations to it, namely R for right, U for up, F for front, L for left, D for down, and B for back. Of course, there are R prime, B prime, and all the other reverse actions of a six-basic operation, but how can we differentiate B from B prime, for example? So to do this, we define that a letter notation without a prime on it to be clockwise. So to decide which direction is clockwise, you can imagine that you rotate the cube, making the surface you want to turn right in front of you, turn it clockwise, and rotate the cube back. This explains why an R action rotates the rightmost layer kind of upward, but an L action rotates the leftmost layer downward. For those who are unfamiliar with this, you can try it yourself on a cube and you'll soon remember it. Okay, based on these notation, let's give another example of reversible operation. Consider we first do U and then do F, and then we notate the two consecutive operations as UF. In order to go back to case 0, we should first offset the effect of F, so we first do F prime, and then we do U prime to offset the effects of U, and we are on case 0 again. And therefore, there's UF composes F prime U prime equals to 0. And here we have the brackets to show that operations within the same brackets are operated at the same time. For example, in the morning we do UF first, but in the afternoon we do F prime U prime. But we then notice that the brackets don't really matter at all, because you can simply do all of these four operations at the same time. So therefore, we can simply write bracket UF composes bracket F prime U prime as UF F prime U prime, and then we can group these operations by any order. So we first notice that F and F prime can cancel each other. So U compose FF prime, then compose U prime. It's just U compose U prime, which is 0 again. And similarly, if we see a long Rubik's Cube formula, like this one on the screen, we can randomly put brackets outside consecutive operations, and that's how professional cubers memorize and analyze these formulas. The arbitrary addition of brackets gives us another simple rule. It's called the associativity rule. That is, for any operation x, y, and z, there's x composed y composed z equals to x composed the result of y composed z. And it's very similar to the associative rule in multiplication. But however, it's not multiplication because it doesn't follow the commutative rule. Because UF is not the same as FU, and you can try it on the cube by yourself. Now I think it's the time for us to introduce the basic axioms of a group. In the beginning, I will say that a group G is a set of objects upon a binary operation. Let's call it cross, that satisfies the following four conditions. And wait, there are so many technical terms need to be clarified. And briefly, a binary operation can be understood as any function that receives two inputs and produce one output. But you can research for a more rigorous definition online. And considering the operations of a cube as a group, we now assume that the set of all objects refers to all permutations of a group. all permutations of a cube, or different patterns of a cube for now. And the binary operation is just composition. And for example, the permutation U and F turns out to be a single permutation U compose F, which is also UF. So the first group axiom is closure. Actually, this axiom is already defined in a binary operation mathematically, but let's talk about it anyway. The closure axiom requires that for any elements A and B in G, A cross B is also in G. This makes sense on a cube because any composition of two permutations is also a permutation. And here the cross sign doesn't really mean that it's multiplication, and rather it's a random sign we pick to notate the binary operation. So we can also omit that sign and denote A cross B as AB. The next axiom is associativity. For any elements A, B, and C in G, there's A cross B, then cross C equals to A cross the result of B cross C. And we have already justified it on a cube that the brackets really don't influence what we get. The third axiom is identity. There exists an element E such that for any element A in G, A times E equals to E times A equals to A. This axiom is a little bit weird, but if you think about the role that 1 has in multiplication, it makes sense that there's an element that will not change the property of an object if you compose the element with that object. In the addition, the identity is 0. In the addition upon all positive integer, or maybe let's say all the integers, because anything plus 0 is still itself. And here on a cube, the identity is just our case 0, which means that you do nothing to the cube. The last axiom is inverse. For any element A in G, there exists an element A prime in G, such that A compose A prime equals to A prime compose A and equals back to E, the identity. This is also true on a cube. There's always a reverse action to offset the original action, and if you do them by order, you literally do nothing to the cube. Finally, there are 4 axioms, 4 necessary conditions that a group must follow for it to become a group. These are closure, associativity, identity, and inverse. And all of these axioms are based on a defined set of objects in a binary operation. In mathematics, the group is just a structure that mathematicians categorize to compare different systems. In their opinion, the structure of the system and the way how the elements react within the system is more important than what these elements really are. And that's why they introduce a group structure to categorize some similar mathematical system. Now let's go back to the cube group. We have already confirmed that all permutations of cubies under composition form a group, but what is exactly a permutation? Consider the following example. If you mistakenly install the Rubik's Cube as if you turn a corner by 120 degrees, is it a permutation? Or can this pattern go back to case 0 without turning the corner back by some simple operations? If no, then this is not a legal permutation, because for it to be a permutation, it must be in a group, and by inverse axiom, it has a reverse action that can turn it back to the case 0, but you cannot just brutally turn the corner back again. And actually, we'll see in some next videos of the series that we cannot turn this back to the case 0, and it's not a legal permutation. So this makes us qualify our original definition of a cube. And now, what can we do to the cube exactly? I would say that all we can do is to conduct URFLDB, such operations of a cube, for a certain number of times and by a given sequence. And for example, an R prime is also formed by these simple operations because R prime is just doing R for 3 times. And this statement is clear from the mechanism of the cube and the rule that you cannot brutally turn a corner or tear down the whole cube. And therefore, it's better to say that the cube group is the set of all permutations that are the combinations of the basic permutations under composition, and the 4 axioms still hold. And now we'll present some examples of groups and non-groups. Here the letter Z denotes all integers, and the letter Q denotes all rational numbers. A Q plus denotes all positive rational numbers. Here we use a bracket to denote the group, which contains the set itself and a binary operation upon it. For example, Z plus is the addition operation on all integers, and you have to check if this operation follows the above 4 group axioms. Can you find out why the first 2 are groups, but why the other 2 are non-groups, or do the latter 2 even make sense? This is the end of the story, and we are now clear about what conditions that a group should satisfy. To explore the other properties of the cube group, please follow the next videos of this series and subscribe me on your YouTube account. Thank you for watching Cubing in a Group, and we'll talk about permutations on the next episode.